Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the Gibbs energy, entropy and enthalpy of mixing when 1.00 mole of C6H14 is mixed with 1.00 mole of C7H16 at 298 Kelvin. This question is from the Atkins Physical Chemistry 11th edition textbook, and it is from chapter 5B, questions 6B. So, what this is telling you is that we need to determine the Gibbs energy, the entropy, as well as the enthalpy of mixing when 1.0 mole of C6H14, which is also hexane, is mixed with 1.00 mole of C7H16, which is heptane, at the temperature of 298 Kelvin. So, as you're aware, as scientists, we have to write out all of the parameters given before we start the solution. So, the first thing we're given is for us to determine the Gibbs energy of mixing. So, we don't know what that is. We're also told to determine the entropy of mixing. Okay. And lastly, we're told to determine the enthalpy of mixing. So, yeah, and then we're actually given the number of moles of hexane. So N sub hex, number of moles of hexane, we're told to be 1.00 mole. And then N sub hept, which we were told to be 1.00 mole. And then, of course, the temperature is 298 Kelvin. So that's basically it. Of course, they've given us all of the parameters. They just want us to determine the Gibbs energy of mixing, the entropy of mixing, as well as the enthalpy of mixing. So when you look at the textbook in this particular chapter, you would see that there are two formulas to determine the Gibbs energy of mixing. So I'm going to start with the Gibbs energy of mixing, then I'll solve for the entropy of mixing, and I'll then solve for the enthalpy of mixing. So looking at our textbook, we see that the Gibbs energy of mixing, okay, has its own formula. Actually, it has two formulas. And the first formula, whenever you're dealing with two components, in this case, components A and B, I'm going to give you the general formula when you have two components, component A as well as component B. You have change in Gibbs energy of mixing is equal to N sub A, so the number of moles of component A multiplied by R multiplied by T, ln P sub A, so the pressure of component A divided by P, okay, which you can also say P total, okay, or just P is the same exact thing, plus N sub B, where B is component B, so N sub B is the number of moles of component B multiplied by R multiplied by T, ln P sub B, okay, divided by P sub T. So P sub B is just the pressure of component B. So yeah, this is it. And then you have the second formula, which is given to us in the textbook, and I'm going to explain when to use each formula. So the change in Gibbs energy of mixing is equal to N sub T, okay, the total number of moles multiplied by R, gas constant, multiplied by T, okay, multiplied by X sub A, okay, multiplied by ln X sub A again, okay, plus X sub B, ln X sub B, close brackets, and just that. So you see N sub T here is just telling us the total number of moles of all of the components. I also want to explain to you that in this case, you can see N sub T just written as N in some formulas. And then you have X sub A, which is just simply the mole fraction, okay, of component A, okay. And then, of course, X sub B is just simply the mole fraction of component B. So that's basically what's going on here. So now you may be wondering, oh my God, which one should I use? There are two of them. I don't know which one to use. It is very, very simple. You have to use the one that is very, very closely related to the parameters that you're given in the question, right? For example, this first one, this first formula, we have the number of moles of each component. We have temperature, which you always be given. You have gas constant, which you always have. And then you have the pressure of each component as well as the total pressure. In a situation like this, you can only use this first formula whenever pressure, okay, is given to you, okay, or can be calculated from the question, or can be calculated from the question. So, for example, in a situation where maybe you're given volume and you're given number of moles and you're given temperature, you can still use this particular formula, because if you're given number of moles, gas constant, temperature, and volume using the ideal gas law, you can simply substitute whatever you need to substitute and determine the value for pressure for each component as well as the total pressure. So use this first formula whenever pressure is given to you or can be calculated from the question. That's how you do the first one. Now, the second one, you may be wondering, when should you use this? You should use the second formula, okay? Whenever number of moles are given. So use this formula when number of moles are given, okay, or mole fraction are given or can be calculated. So in a situation where you're given pressure and volume and you are not given any number of moles, you cannot use the second formula. You need the number of moles of each one of the components to be given to you, or you can calculate the number of moles of each one of the components from the question that you're given. So in this case, either they give you the number of moles or they give you the mole fraction. Of course, when you now go back to our question and read it, we're told to calculate the Gibbs energy, entropy, and enthalpy of mixing when 1.0 mole is mixed with 1.0 mole. You can see that we're going to use the second equation because we're given the moles, as well as we can easily calculate the moles if we weren't given, but in this case, we're given the moles and we can easily calculate the mole fraction since we already have been given the moles of all the components. It's not going to work for the first formula because we're not given any information with regards to pressure. Either way, we're given volume that can be used to calculate pressure. So if this is a mouthful for you or an earful, please, for the sake of God, pause it, rewatch it, or watch it all the way through and then rewatch it again. I think when you watch it at least twice, you should be fine in understanding what I'm doing. And of course, with more practice, you're going to be able to see that this is not a hard thing to follow. So we're going to be using the second formula. So rewriting the second formula, we have change in mixture of G, or change in Gibbs energy of mixing, is equal to N sub T, again, N total multiplied by RT, okay, multiplied by X sub A, so the mole fraction of component A, ln X sub A, okay, plus X sub B, ln X sub B. So this is the formula that we're going to use. Now, the question, of course, told us that we're going to be working with hexane as well as heptane. So I'm going to update this new formula in the form of our actual question. So change in Gibbs energy of mixing, simply N sub T, so total number of moles multiplied by R multiplied by T, X sub hex, okay, for hexane, multiplied by ln X sub hex multiplied by hexane, sorry, X hex meaning hexane, plus X sub B, in this case, B is just simply heptane, so HEP, okay, ln X sub hep as well. So yeah, this is basically what's going on. So change in Gibbs energy of mixing is simply going to be the total number of moles, R times T, and then you got ln, all of this. So R times T, then multiply, so the total number of Gibbs energy of mixing would just be us substituting each one of these parameters. So now we go back to our work. We see that we're told to use N total. We do not have N total, but what N total simply is just simply N total is just simply adding the total, adding the value for N sub X plus N sub hep, meaning you add the total number of moles. In this case, we have the total number of moles. Just looking at it right here, we have the number of moles of hexane. If we go back up, we have 1.0 mole, and then the number of moles of heptane is also 1.0 mole. So 1.00 mole plus 1.00 mole. So that's just simply 2.00 mole. So that's basically what that is. And then, of course, we have to determine what the mole fraction of hexane is. So the mole fraction of hexane is just going to be the number of moles of hexane divided by the total number of moles. And we know the number of moles of hexane is just simply 1.00 mole, okay, divided by the total number of moles, which is just 2.00 mole, okay. That's just that one. So, of course, you cancel out the mole. Cancel out the mole. What you end up with is 1 over 2, or just simply 0.500. So that's what that value is. We do the exact same thing that we did for heptane. So mole fraction of heptane is just simply going to be the number of moles of heptane divided by the total number of moles, So you have 1.00 mole divided by 2.00 mole. Cancel out the mole here. Of course, 1 over 2 is just simply 0.500 mole. And I'm trying to maintain the number of significant figures just because we're used to keeping the proper number of significant figures in questions like this, just because we're doing a chemistry question. So anyways, so you have these two values. So now that you have the total number of moles to be 2.0 mole, you have the information for mole fraction for hexane as well as the information for the mole fraction of heptane. You can just simply substitute. Okay. So again, rewriting it. I know we've written it so many times at this point. Rewriting the Gibbs energy of mixing. Okay. You have n sub t. Okay. R t x sub hex ln x sub hex plus x sub hep ln x sub hep. So you have change in mix of G is just simply, okay, the total number of moles is just 2.00 mole, okay? So you have 2.00 mole multiplied by, you have R, which is just simply the gas constant. And of course, we're going to be using the 8.3145 because of it has the units joule per mole Kelvin. And because Gibbs energy has the units of joules, normally we have to maintain that. We cannot use the other gas constant, which is 0.08206, because it doesn't have the proper units that we're going to need at the end of the day. So anyways, we're going to be using the 8.3145 joule per mole Kelvin because we need those joule, okay, as a unit for this changing Gibbs energy of mixing. So that's very, very important. You guys will only know this by consistent practice, honestly. Multiplied by the value for temperature. Go back up. Value for temperature is 298 Kelvin. So multiply by 298 Kelvin. All of that information multiplied by the mole fraction of hexane, which is just 0.500 ln 0.500, okay, plus the one for heptane, the mole fraction is 0.500 as well. So 0.500 ln 0.500. So that's it. So change in Gibbs energy of mixing is simply 2 times 8.3145 times 298 Kelvin. When we input that in our calculator, we end up getting 4,955.422. Now, of course, we have to put the proper units for this part. We have to cancel out the mole here, cancel out the mole here, cancel out the Kelvin here, cancel out the Kelvin here. What we have here that is left is just simply joules. So that joules multiplied by the information on this side as well as adding it to the information on this side. So multiply by 0.500, okay, ln 0.500. When you input that in the calculator, you're supposed to get 0.34657,359. So this is what you get for this left side, the one left of the positive sign. And then, of course, plus 0.500 ln 0.500 is simply the exact same value. So you end up with plus negative 0.34657,359. So that's it. Of course, positive and negative here is just going to make it negative. So yeah, this is just simply it. So change in Gibbs energy of mixing simply just going to be 4955.422 joules multiplied by negative 0.34657,359 minus 0.34657,359. It's just basically multiplying both of them by 2. So when you do that, you end up with just negative it's just basically multiplying the value by 2. You just basically are adding the exact same thing, but with a negative sign. So you end up with negative 0.6931472. So that's basically what that is. And then in change in Gibbs energy of mixing, simply when you multiply this left side which is 4955.422 by negative 0.693142, you end up with negative 3434.850651 joules. So this is what you end up getting as the answer for the Gibbs energy of mixing. But of course, we are scientists. We have to put our work in the proper number of significant figures. So we have to go back to our question and see the lowest number of sig figs. The lowest number of sig figs in this particular question is 3 sig figs. So our final answer has to be written in 3 sig figs. So changing Gibbs energy of mixing just ends up becoming negative 3.43, okay, times 10 raised to the power of 3 joules, or negative 3.43 kilojoules. And this is basically the answer to the Gibbs energy of mixing. So yeah, this is it. Our work is still not done. We still have 2 more questions to answer. So as you can see, the question asks us, if we go back to the top, we need to know the entropy of mixing as well. So the entropy of mixing, which is what we're supposed to look for here, if simply entropy of mixing can actually be calculated from the Gibbs energy of mixing. So that would just simply be negative, open bracket, the Gibbs energy of mixing. Okay, so we can use the Gibbs energy of mixing to determine the entropy of mixing answer divided by temperature. So that is just it. So it's just us knowing that there's going to be a negative sign in front of the Gibbs energy of mixing divided by whatever the temperature was to begin with. So yeah, so that's just it. So of course we substitute the raw value of the Gibbs energy of mixing. We know that to be negative 3434. So okay, so negative 3434.850651 joules divided by 298 Kelvin. Now you may be wondering, why don't we just substitute negative 3.43 times 10 to the power of 3 whenever you're dealing with a question and you're supposed to be using that same answer that you had solved before for further calculation? You're going to use the raw value. Use only when you get to the final answer that you can start approximating things to 2 decimal places, 2 significant figures, any number of significant figures of any number of decimal places. You can only do that at the very end. But if you're using the same value, raw value in calculation, stick to using the raw value, not the approximated value, in order for you to get your answer very correct. You see the value of this only in multiple choices, because in multiple choice question, you actually need an exact value. But your calculation, you're going to actually lose points for using the approximated value rather than the raw value. So negative is of course positive. 343.850,651 joules divided by 298 Kelvin would just simply give you 11.52634.5 joule per Kelvin. And of course, we have to put work in the lowest number of significant figures. So really, the change in Gibbs energy, the change in entropy of mixing ends up just simply becoming positive 11.5 joule per Kelvin. And this is basically the answer to this particular part of the question. Then, lastly, we're also told to determine the enthalpy of mixing. So the enthalpy of mixing, okay, so the enthalpy of mixing is what we're supposed to do next. And remember, what did the question also say? Calculate the Gibbs energy, blah, blah, blah. It's the same exact thing. Now, I want to quickly mention to you that all that we're working on in this particular question is based on ideal solutions, okay? We are dealing with ideal solutions here. Therefore, in ideal solutions, no heat, okay, is absorbed or transferred, causing our enthalpy to equal 0. So the change in enthalpy of mixing is always 0 for ideal solutions, since there is an absence of heat transfer. So that's just basically it. The change in enthalpy of mixing is always going to be zero for ideal solutions. So it is unaffected because in order for us to even work on enthalpy, we have to have a situation where there is heat transfer going back and forth. And of course, if heat is equal to zero, then um or there's no heat transfer, there's no value for heat transfer, the enthalpy is automatically equal to zero. So that's basically how you solve that last one. If you have any questions, suggestions, or concerns, please put in the comment section. If you're still struggling with what I solved, note that there's going to be another similar question like this. And I would also advise you to not only watch this video more than once, I would also advise you to watch the other video maybe more than once as well. I think if you've seen this material, at least 3 to 4 times, I think you would understand it very, very well and you feel more confident. There's also another third and fourth question, but in those cases, we deal with pressure and volume, not the number of moles. So I would urge you to also watch those. All of this is from the Atkins Physical Chemistry 11th edition and on my channel. I also want to mention lastly that if you're a student who is struggling in any of your STEM related courses, I tutor students not just for physical chemistry, but all range of STEM related courses, whether you're in middle school, high school, university, or college. So do not hesitate to email me if you want to succeed in academia, and I would help you by my way of tutoring and mentorship. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.